We are going to start module 4 of chapter 10. In this module, we shall discuss the force and energy in relativistic mechanics. Our earlier theory explains the experimental facts accurately when the velocity involved there is much less than the speed of light, but it cannot explain the experimental facts when the velocity involved there approaches to the speed of light. This theory is known as relativistic mechanics. Later on, Einstein in 1905 proposed some postulates. These postulates and their consequences develop the special theory of relativity. It explains the experimental facts accurately when the velocity involved there approach the speed of light. This belongs to relativistic mechanics. In this module, we shall discuss the force and energy in relativistic mechanics. First of all, we shall obtain the expression for force and then the expression for energy in relativistic mechanics will be obtained. Using the expressions, we shall deduce the relation between energy and linear momentum in this module. First of all, let us discuss about the force in relativistic mechanics. In our earlier mechanics, that is non-relativistic mechanics, the linear momentum of a particle is defined as p vector is equal to mass into velocity vector. That is, if m be the mass of the particle moving with velocity v vector, then linear momentum of that particle is given by p vector, which is m into v vector. Let us now define the force. If capital F vector denote the applied force on the particle of mass m moving with velocity v vector, then force is defined in non-relativistic mechanics as F vector is equal to mass into acceleration. We know that acceleration is nothing but the time rate of change of velocity vector, that is ddt of v vector gives the acceleration vector. So, F vector is equal to ddt of m into v vector, that is ddt operated on linear momentum p vector. As m is constant, we get F vector equal to m into ddt of v vector. We have already mentioned that acceleration F vector is ddt of v vector. So, we get capital F vector is equal to mass into acceleration F vector. Here we have used force is equal to time rate of change of linear momentum. We get it from Newton's laws of motion. Small f vector is the acceleration of the particle having mass m, and capital F is the applied force on the particle. Let us consider the relativistic mechanics. What will be the form of linear momentum in relativistic mechanics. Let us discuss about it. In relativistic mechanics, linear momentum p vector is defined as m into gamma into v vector, where gamma has the expression like this. Here v is the uniform velocity with which frame S dash is moving along the common direction of x and x dash axis, while c is the speed of light. Thus, the force in relativistic mechanics is given by F vector equal to ddt of linear momentum, that is ddt of m into gamma into v vector. Now, we take the derivative. Here we consider m gamma as one variable and v as another variable. Then first of all we take m into gamma as fixed and take the derivative of v vector with respect to time t and get this term. And here taking v vector as fixed, we take the derivative of m into gamma. Please note that m is constant, so we get m into v vector into ddt of gamma. Gamma contains v, so we are considering ddt of gamma. If we denote the component of acceleration vector, that is ddt of v vector, along the x axis as dv dt parallel is equal to f parallel. F is the acceleration, while the perpendicular component of ddt of v vector as perpendicular component of acceleration, that is f perpendicular. This gives the component of acceleration along perpendicular direction of x axis. Then from here we get the perpendicular component of force F vector is F vector perpendicular, which is equal to m into gamma into perpendicular component of ddt of v vector. We get it from here. So, denoting ddt of v vector perpendicular as f vector perpendicular, we get this result. We can also obtain the parallel component of force vector, that is f vector parallel, which can be obtained from here also, just putting the parallel component of ddt of v vector and parallel component of v vector, we get this result. Denoting ddt of v vector parallel equal to f parallel, we get this result, where gamma is given by gamma equal to 1 divided by square root of 1 minus v square divided by c square. Let us calculate ddt of gamma. Ddt of gamma is equal to 1 divided by c square into 1 minus v square by c square whole to the power half plus 1, that is 3 by 2 in the denominator, and taking the derivative of this term, we get v vector dot ddt of v vector. Negative signs cancels each other. We get the negative when differentiating square root of 1 minus v square by c square, and again differentiating v square by c square, we get one negative sign. Both negative signs cancels and we get this result. Here v vector dot ddt of v vector gives the dot product or scalar product between two vectors. Using the property of dot product, we get v vector dot ddt of v vector is equal to absolute value of v vector into absolute value of ddt of v vector into cos of angle between these two vectors, that is v vector and ddt of v vector, which is theta. So, we get this result. Here theta is the angle between two vectors v vector and ddt of v vector. Now, ddt of v vector with its magnitude into cos theta gives the parallel component of acceleration vector, that is f vector parallel. So, ddt of gamma becomes this one. Substituting ddt of gamma in the expression for force vector, we get the parallel component of force vector equal to this one. This can be combined like this. Here we have used that parallel components of v vector is small v and get this result. Here we have substituted the value of gamma here, and on simplification we get this result. Thus, we have parallel component of force vector is equal to m into gamma cube into parallel component of acceleration vector. We have already obtained the perpendicular component of force vector, which is m into gamma into perpendicular component of acceleration vector. Please note the difference between the parallel and perpendicular components of force vector. M into gamma cube may be defined as the longitudinal mass, that is the mass in the direction of motion of the object, while m into gamma gives the transverse mass. Our common sense tells that mass remains unchanged during motion, but in relativistic mechanics we have already shown that mass depends on velocity and changes during its motion. Using this fact, we have obtained the expression for force in this module. Now, using the same phenomena, we shall obtain the expression for energy. Let us discuss the energy. We have already defined the linear momentum. The linear momentum of mass m moving with velocity u vector is given by p vector is equal to m into u vector, mass into velocity. This is the definition of linear momentum in non-relativistic mechanics. We know that the mass changes like this. Substituting this here, we get p vector is equal to m0 into u vector divided by square root of 1 minus u square divided by c square. Please note that so far we have an idea that mass remains unchanged in motion, that is, mass is independent of velocity, but here in relativistic mechanics mass changes like this. Now, force F vector is the time rate of change of linear momentum, that is ddt of small p vector, where F vector is the force acting on mass m. In relativistic mechanics, kinetic energy T can be defined as follows: ddt of T is equal to F vector dot u vector. Here dot means we are considering the dot product of two vectors or scalar products of two vectors. F is the force vector, u vector is the velocity vector. We know that kinetic energy is equal to half into m into u vector square. Taking the time derivative, we get m into u dot ddt of u. M into ddt of u gives force vector and we have another u. So, we get ddt of capital T is equal to F vector dot u vector. We have already obtained that F vector is ddt of p vector, where p vector is the linear momentum. Substituting this, we get this result. If we substitute the relation between p vector and velocity u vector, we get this expression. Taking the derivative, we get this result. Here at first we have calculated the derivative of numerator, keeping denominator unchanged. Then the taking numerator fixed, we have obtained the derivative of denominator here and get this result. On simplification, we get the last line, an integrating constant. We have to find the value of the integrating constant. In finding its value, we can use the initial condition, which is when u equal to 0, that is initially when the object is at rest, then obviously kinetic energy T equal to 0. Since we know that kinetic energy T is equal to half into m into u square. So, when u becomes 0, T becomes 0. Substituting these in the previous equation, we get the value of the integrating constant C dash as C dash equal to minus m suffix 0 into c square. If we substitute the value of C dash, we get the expression for kinetic energy T in relativistic mechanics. This result can be combined like this one. Let us consider the case when u less than c. Then kinetic energy T can be written in this form, T equal to m0 into c square 1 divided by square root of 1 minus u square by c square can be written as 1 minus u square by c square whole to the power minus half, and multiplying minus 1 with m0 c square we get minus m0 c square. If we expand this term, then we get capital T equal to m0 c square into 1 plus half into u square divided by c square plus terms of order u divided by c whole to the power 4. This term has been written as it is. As u less than c, so we can neglect these quantities, these are of higher powers, so negligible. Then we retain these two terms. Multiplying m0 c square with 1, we get m0 c square, and here we get minus m0 c square. So both cancels each other. We finally get capital T equal to half into m0 into u square. Here m0, 0 is in suffix, denotes the mass of the particle. This gives the result for non-relativistic mechanics. This is the expression for kinetic energy in non-relativistic case, whereas this is the expression for kinetic energy in relativistic mechanics. Let us obtain the relation between energy and momentum. Energy in relativistic mechanics is given by capital E equal to m into gamma into c square, whereas linear momentum in relativistic mechanics is p vector equal to m into gamma into v vector. Gamma is of the form like this. Let us calculate capital E square minus p square into c square. Let us substitute the value of E and P, then we get this result. After some simple calculation, we get this one. Putting the value of gamma, we get E square minus P square into C square is equal to m square into c to the power 4. Thus, shifting this term on the right hand side, we get capital E square equal to P square into C square plus m square c to the power 4. Newton's laws of motion provide accurate result when the velocity involved there is much less than the speed of light. But when the velocity approaches to the speed of light, these cannot explain the experimental facts correctly. This theory belongs to non-relativistic mechanics. In those cases when the velocity involved there approaches the speed of light, we need a general theory which is known as special theory of relativity. This belongs to relativistic mechanics. In this module, we have obtained the expression for force, energy and linear momentum in relativistic mechanics and have shown that these expression coincides with the expression obtained in non-relativistic case in the limit of low speed.